For all of human history, something enormous has been quietly sitting in the dark above us, and almost nobody knew what they were looking at. It is a galaxy called Andromeda, bigger, stranger, and closer than most people realize. Today we find out just how large it truly is, what is happening inside it right now, and why its arrival will change everything. Now let's begin. Right now, something is heading straight toward Earth. It contains 1 trillion stars. It has been moving in our direction for longer than our species has existed. It cannot be stopped, cannot be redirected, and no force in the known universe will slow it down. And here is the part that will genuinely unsettle you. If you walk outside tonight and the sky above you is dark enough you can see it with your own eyes, no telescope, no special equipment, just your eyes and a clear night. It is not a comet trailing fire across the sky. It is not a rogue black hole drifting through the dark. It is an entire galaxy intact and immense, moving toward us at 110 kilometers every single second. Its name is Andromeda, and it has been there above us every night of every year of every generation of human history. Kings looked up and saw it. Farmers read the seasons beneath it. Children lay in fields and stared at the sky, without ever knowing that one of those faint smudges was another galaxy entirely. Most of them never knew, and honestly, most of us today still do not notice it either. When you find Andromeda for the first time with your naked eye, the experience is nothing like what you might expect. There is no dramatic glow, no sweeping arc of light cutting across the sky. What you see is quiet and almost apologetic, a soft blur, slightly oval, sitting still among the stars. It does not sparkle the way stars do. It does not move like a planet. It simply rests there at the edge of visibility, easy to overlook, easy to dismiss, as a patch of haze or a wisp of thin cloud that somehow got left behind. That modesty is one of the strangest things about it, because what you are looking at in that moment, that small, unremarkable smear of pale light, is the combined glow of 1 trillion stars. Every single photon reaching your eyes has traveled for 2.5 million years across empty space to end its journey here, in this moment against the surface of your retina. The light is ancient, the source is enormous, and yet, to the naked eye, it looks like almost nothing at all. This is the first great paradox of Andromeda. It is the largest object a human being can see with unaided eyes anywhere in the universe, and it looks more humble than a mid-level star on a busy night. A star that might be 50 times smaller and 1,000,000 times closer will outshine it completely. Andromeda, with its trillion suns, barely registers. The reason for this lies in how our eyes work and how light behaves across distance. What your eyes actually pick up when you look at Andromeda is only the central region, the bright and densely packed core, where billions of older stars are crowded together closely enough to produce a visible glow. The rest of the galaxy, its sweeping spiral arms, its vast outer disk, its enormous halo of faint stars stretching far beyond the main body, all of that is spread across a patch of sky more than 6 times wider than the full moon. 6 times. If your eyes were sensitive enough to gather all of that light at once, Andromeda would dominate the night sky in a way that nothing else comes close to matching. It would be impossible to ignore, but our eyes are not built that way. The outer regions are too diffuse, the light spread too thinly across too large an area, so instead of a galaxy we see a smudge. The rest is there falling on us continuously but invisible. For thousands of years, people who wanted to see faint objects in the sky discovered something counterintuitive through trial and patience. If you look directly at something dim, it often disappears. But if you shift your gaze slightly to one side and let the object fall on the edges of your vision rather than the center, it suddenly becomes visible again. This technique has a name: averted vision. It works because the outer regions of the human eye are more sensitive to low levels of light than the central part. Stargazers across centuries, long before anyone had a name for the method, figured this out simply by spending enough time in the dark and paying careful attention to what their eyes were telling them. Andromeda rewards that kind of patience. When you stop staring directly at it and let your gaze drift slightly away, the blur sharpens ever so slightly. It becomes more real, more present. And in that moment, something shifts. There is a particular quality to the experience of finding Andromeda for the first time and understanding what you are actually seeing. It tends to arrive quietly, not as a dramatic revelation, but as a slow settling of something into place. You are standing on the surface of a planet, looking up through the thin shell of an atmosphere, and your eyes are gathering light that left another galaxy before your species walked the Earth. The blur you are looking at is not a cloud. It is not a reflection. It is 2.5 million light-years of distance compressed into a faint oval that fits inside your field of vision. Everything you have ever known, every civilization, every story, every war and discovery and love and loss in all of human history happened in the time it took that light to reach you. That is the moment when the smudge stops being a smudge. It becomes something else, a presence. A neighbor that has always been there, patient and enormous and mostly invisible, waiting for someone to look in the right direction with the right kind of attention. Have you ever looked up at the night sky and paused at a faint blur, wondering for just a moment whether it was something more than it appeared? Andromeda is hiding in plain sight above us every clear night, and the reason your eyes cannot take in the full scale of it connects directly to something. Far more unsettling, the actual size of this galaxy is a number so large that when you truly try to hold it in your mind, something in your thinking quietly gives up. 220,000 light-years, 1 trillion stars, a central black hole weighing 100 million times the mass of our Sunday. 3 numbers, and not one of them means anything to the part of your brain that was built for navigating rivers, reading weather, and judging distances across open ground. The human mind is extraordinarily good at scale within a certain range. We understand meters and kilometers. We can feel the difference between a short walk and a long one, between a small room and a wide open field. We can even stretch with some effort to grasp the size of continents or the depth of oceans. But then the scale of the universe arrives and something breaks. The numbers keep coming and the comprehension quietly stops. So instead of simply stating the measurements and moving on, it helps to build upwards slowly, one step at a time, and feel the ground drop away beneath you as you go. Start with something familiar. The distance from Earth to the Moon is roughly 380,000 kilometers. Spacecraft have crossed it. Humans have stood on the Moon and looked back. That distance feels, at least in some abstract sense, almost reachable. Now multiply it by about 400, and you have the distance from Earth to the Sunday light covers that distance in 8 minutes. A commercial aircraft flying without pause would take more than 20 years. Already we have left the territory of intuition behind. Keep going. The nearest star to our sun, Proxima Centauri, sits about 4 light-years away. That means the light from it takes 4 years to reach us. The fastest spacecraft ever launched by humanity, traveling at tens of thousands of kilometers per hour, would need roughly 70,000 years to make that journey. And Proxima Centauri is our closest stellar neighbor. It is practically next door. Now step back and look at the full width of our own galaxy, the Milky Way. From one edge to the other, it spans somewhere between 100,000 and 120,000 light-years. That is a distance so vast, even light traveling at the absolute speed limit of the universe takes over 100,000 years to cross it. Andromeda is nearly twice as wide, 220,000 light-years from one edge of its disk to the other. If you shrank our entire solar system from the Sun out to the farthest reaches where comets drift in the cold dark down to the size of a small coin, Andromeda, at the same scale, would stretch across the entire continent of Asia. Not a city, not a country, a continent. The star count pushes things further into territory where numbers stop feeling like numbers. 1 trillion stars. To count them at a rate of 1 per second, without sleeping, without stopping, would take more than 31,000 years. You would need to have started counting before the last ice age ended, continue through the rise and fall of every civilization in history, and still not be finished today. And here is the part that quietly undoes the whole exercise. By the time you reached the end of your count, the list would already be wrong. New stars would have formed inside Andromeda while you were counting the old ones. The galaxy does not wait. Then there is the black hole sitting at the center of all of this. It carries a mass equivalent to 100 million suns. Our own galaxy has a central black hole as well, a presence known as Sagittarius A star, which weighs in at around 4 million solar masses. That already sounds impossibly heavy. But Andromeda's central black hole outweighs it by a factor of 25. It is a different category of object, entirely sitting in the heart of the galaxy like an anchor the size of a small god. There is something almost funny about the progression of discoveries here. For centuries, humans assumed Earth was the center of the universe. Then we discovered it orbited the Sun. Then we found the Sun was one unremarkable star among hundreds of billions inside the Milky Way. Then we realized the Milky Way itself was just one galaxy among hundreds of billions more scattered across observable space. And then, as if to drive the point home one final time, we looked at our nearest large neighbor and discovered it was twice our size with a black hole, 25 times more massive than our own. The universe has a particular patience when it comes to reminding us of our actual position in things. But perhaps the most disorienting part of Andromeda's true scale is the part you cannot see at all. Surrounding the visible disk of stars and dust is an enormous halo of dark matter, a region of invisible mass that does not emit light, does not reflect light, and cannot be detected by any telescope tuned to any wavelength. It can only be inferred from its gravitational effects on the things around it. This halo extends more than 1 million light-years outward from the center of Andromeda in every direction. That means the invisible portion of the galaxy is larger than the visible portion by a significant margin. What you see when you look at Andromeda, that pale smear in the sky, that bright central disk that spans 220,000 light-years, represents only a fraction of what is actually there, and the boundary of even that invisible halo is not a clean line. There is no edge where Andromeda ends and empty space begins. The density of matter simply decreases, gradually and continuously fading outward into the surrounding darkness, the way morning fog dissolves into daylight. No one can say precisely where Andromeda stops. The question itself may not have a clean answer. This is what the numbers are pointing at. Not just a large object, but a system so vast that even its borders are uncertain. So massive that most of its weight is hidden, so populated that counting its contents would outlast recorded history many times over. Does the human brain truly understand 1 trillion, or does it simply process the phrase and move on? Those numbers describe only the size of what is there. But inside Andromeda, things are happening that ordinary visible light will never reveal on its own, and to see them, science had to learn an entirely new way of looking. Andromeda is not a painting hanging still in the dark. It is not a fixed object frozen in space, waiting patiently for someone to admire it. It is a system in constant motion, constantly consuming and creating, breathing in gas and breathing out starlight, giving birth to new suns and watching old ones collapse and die. Everything inside it is in the middle of something. Nothing is finished. Nothing is at rest. To understand what Andromeda actually is, it helps to move through it from the outside in, layer by layer, the way you might peel back the structure of something living to find what keeps it going. The outermost layer is the one you cannot see at all. It is the dark matter halo, an enormous, invisible sphere of mass that surrounds the entire galaxy and extends more than 1 million light-years in every direction. No telescope can image it directly. It produces no light, reflects no light, and interacts with almost nothing except gravity. And yet without it, Andromeda would not hold together. The visible stars in the outer disk orbit far too fast to remain bound by the gravity of the stars alone. Something else is holding them in. That something is the halo unseen and unmeasured in any direct sense, but undeniably present in everything it shapes. Moving inward from the dark matter halo, you encounter the stellar halo, a sparse and ancient cloud of individual stars that drifts far beyond the main disk. These are mostly old stars, quiet and dim, some of them relics from the earliest period of the galaxy's formation. They do not form neat patterns or organized arms. They simply float loosely in a great diffuse sphere around the galaxy's main body. Among them, if you look carefully with a powerful enough telescope, you find long, thin streams of stars arcing through the darkness, each one the remnant of a smaller galaxy that wandered too close and was slowly torn apart by Andromeda's gravity over hundreds of millions of years. Then comes the disk, and within the disk the spiral arms. This is where Andromeda becomes visually extraordinary. The arms sweep outward from the central region in broad, curving arcs, and from a distance they look like solid structures, like the arms of a pinwheel caught mid-spin. But they are not solid at all. They are not walls of stars that stars are locked inside. They are something more subtle and more interesting than that. They are patterns, regions where matter happens to be more concentrated at any given moment. Stars drift into them slightly as they move through the denser region and then drift out the other side. The arm itself persists, but the individual stars within it are always changing. It is the same principle as a traffic jam on a long highway. The jam stays in one place while the cars that compose it are continuously moving through and beyond it. In Andromeda, those traffic jams have been maintaining their shape for billions of years, driven by waves of gravitational density rippling through the disk. Color becomes a language inside the spiral arms. Where the arms shine blue, young massive stars have recently ignited, burning hot and bright, pouring out intense ultraviolet radiation that illuminates the surrounding gas. These stars live fast and die young, lasting only a few million years before exploding as supernovae. Where the light shifts toward yellow and orange, older and cooler stars dominate populations that have been burning steadily for billions of years. And threading through all of it, the dark lanes regions where thick clouds of dust and gas absorb the light behind them and appear as shadows cutting across the arms. Those dark lanes are not empty. They are full of material, the raw ingredients from which the next generation of stars will eventually form. What ordinary visible light reveals is already remarkable. But visible light is only one narrow slice of the full spectrum of radiation. And when astronomers turned instruments tuned to other wavelengths toward Andromeda, the galaxy revealed things that had been completely hidden before. The Spitzer Space Telescope and the Herschel Space Observatory, both designed to detect infrared radiation, showed Andromeda in a way that no optical telescope ever could. In infrared, the dust that appears as dark, obscuring lanes in visible light begins to glow with its own warmth. And what those instruments revealed was unexpected. Instead of the smooth spiral structure visible in optical images, the infrared view showed a series of enormous rings of dust, concentric features sweeping around the galaxy's center. These rings are not part of a standard spiral structure. They are the kind of pattern that forms when something large has disturbed a galaxy from outside, sending waves rippling through the disk, the way a stone dropped into still water sends rings outward from the point of impact. The leading explanation is that Andromeda experienced a significant collision with one of its companion galaxies in the distant past, and those rings are still propagating through the disk billions of years later, a slow-motion echo of an ancient impact. The Galaxy Evolution Explorer, an ultraviolet telescope, mapped the regions where the youngest and hottest stars are actively forming, tracing the living edge of starbirth across the disk in a way that visible light alone would never show clearly. Ultraviolet radiation pours out of regions where massive new stars have just switched on, and those regions glow with an intensity that marks them as the galaxy's most actively renewing zones. The Chandra X-ray Observatory added another layer entirely. In X-ray light, Andromeda reveals its most violent processes. The expanding shells of material thrown outward by supernova explosions show up as bright rings of hot gas. Binary star systems, where one compact dead star is pulling material from a living companion, flare and pulse. The region around the central black hole, though currently quiet by the standards of active galaxies, still produces faint X-ray emissions that confirm the presence of extreme physics at the galaxy's core. The universe that looks serene in a long-exposure photograph is in X-ray light, full of ongoing violence. One detail that stands out when all of these views are combined is the asymmetry of Andromeda's spiral arms. They are not mirror images of each other. One arm is broader, more diffuse, and slightly displaced from where a perfectly symmetrical spiral would place it. The other shows signs of having been pulled or compressed. These irregularities are the fingerprints of history. Every close encounter Andromeda has had with other galaxies over billions of years has left a mark somewhere in its structure. The shape of the galaxy today is not simply the result of orderly formation. It is the accumulated consequence of billions of years of gravitational interactions, disturbances, and absorptions. When you layer all of these views on top of each other, the optical image, the infrared rings, the ultraviolet star-forming regions, the X-ray violence near the core, Andromeda stops being a single object and becomes something closer, to a document. Each wavelength is a different chapter. Each reveals something the others cannot. Together they tell the story of a galaxy that is ancient and still changing, settled in its large-scale structure, and yet continuously rearranging itself at every smaller scale. If your eyes could receive every wavelength of light at once, what do you think Andromeda would look like stretched across the night sky above you? Everything we have just seen, every layer of structure, every color and shadow and glowing ring, represents Andromeda not as it exists right now, but as it existed 2.5 million years ago. Because the light reaching your eyes tonight left that galaxy before our species existed. And that single fact changes the nature of everything we think we know about what we are looking at. When you look at Andromeda tonight, you are not seeing it as it is. You are seeing it as it was 2.5 million years ago. At the moment that light began its journey toward us, there were no modern humans on Earth. There was no language, no fire in any controlled sense, no tools beyond the most basic shaped stones. The ancestors of our species were navigating a world that would be unrecognizable to us now. And the galaxy you see above you tonight is the galaxy that existed in their sky, the same image sent outward into space, long before anyone was here, to eventually receive it. This is not a poetic way of describing something. It is a precise and literal statement about how light and distance interact. Light travels faster than anything else in the universe, covering nearly 300,000 kilometers every second. That speed is so extreme that within our daily experience it seems instantaneous. Flip a switch and the room lights up. Look at something across a field and you see it immediately. The delay exists, but it is so small as to be entirely irrelevant. But scale that delay up across the distances of space and the situation changes completely. Light from the moon takes just over 1 second to reach Earth. Light from the sun takes about 8 minutes. Light from Proxima Centauri, our nearest stellar neighbor, takes a little over 4 years. By the time you're looking at stars in the night sky, the delays are already significant. Some of the stars you see tonight are showing you light that left them decades or centuries ago. A few of the brightest stars visible to the naked eye would take their light thousands of years to arrive. Andromeda is 2.5 million light-years away. Every photon you receive from it tonight has been traveling for 2.5 million years. The image you see is not a live view. It is a recording playing back to you across an unimaginable gulf of time. To feel the weight of this concretely, consider what was happening on Earth when that light departed. Our species, Homo sapiens, did not yet exist in any form that modern science would recognize. The early ancestors present at that time were making and using simple stone tools, living in small mobile groups with no evidence of the complex symbolic communication we call language. Fire was not yet a controlled technology. Agriculture was not a concept. Writing civilizations, cities, everything that we typically mean when we use the word history, all of that lay millions of years in the future. The light you see when you look at Andromeda tonight left its source before any of that existed. There is a consequence of this that sounds almost impossible until you sit with it long enough. If Andromeda were to suddenly, completely and catastrophically cease to exist at this very moment, if every star in it were extinguished and the entire structure dissolved into nothing in an instant, we would have no way of knowing. The sky tonight would show us Andromeda exactly as it appears now. Tomorrow night, the same. For the next 2.5 million years, Andromeda would continue to appear perfectly normal in our sky, still glowing, still present, still sending us its ancient light, even though the source of that light had been gone for generations, beyond counting. We would be watching something that no longer existed. receiving its last message on a delay so long that the concept of urgency becomes meaningless. This is not unique to Andromeda. It is true of everything we observe in the universe. Every telescope image ever taken is a historical document. Every galaxy survey is an archaeology of light. The further out into space you look, the further back in time you see. Astronomers studying the most distant galaxies detectable by current instruments are observing those galaxies as they existed only a few 100 million years after the universe itself began. The universe in those images is young and barely formed. Looking at Andromeda is looking at a relatively recent chapter by comparison, but 2.5 million years is still a span of time that dwarfs the entirety of recorded human civilization many times over. Every clear night, new photons from Andromeda arrive at Earth. Not the same photons from the night before, but a fresh set, each one having begun its journey at the same point in the galaxy's past, carrying the same 2.5 million year old information. They arrive continuously like letters from a correspondent who wrote them all at once an immense time ago and whose delivery system has been faithfully sending them ever since one batch per moment, never missing a clear night. The photons that reach your eyes on any particular evening are yours alone in a specific sense. They enter your eyes, they stimulate the cells of your retina, they trigger the signals that your brain processes into the experience of seeing, and then they are gone. Those particular photons, which traveled for 2.5 million years through the cold emptiness of intergalactic space, end their journey at that single point. They do not bounce on to someone else. They are absorbed, their energy spent, their long voyage complete. You are the last thing they ever encounter. What this means at a deeper level is that the universe does not have a single shared present tense. There is no moment that is simultaneously now for everything everywhere. When physicists describe this carefully, they say that simultaneity is relative, that the concept of two events happening at the same time only has meaning within a specific frame of reference. For practical purposes, in daily life, this is irrelevant, but across the distances of intergalactic space, the effect becomes impossible to ignore. Andromeda is living in its own present 2.5 million years ahead of the image we see. We are observing its past while it continues into a future we have no access to yet. If a civilization existed somewhere within Andromeda and possessed a telescope of sufficient power to resolve detail on Earth across 2.5 million light-years of space, what would they be looking at right now? They would not see cities. They would not see evidence of industry or communication or any of the markers of technological civilization. They would be observing Earth as it was 2.5 million years ago, a planet with no humans on it in any recognizable sense, its continents shaped slightly differently, its climate in a different configuration. Whatever they found interesting to observe about our world, it would not be us. Light has carried the entire story of Andromeda to us across 2.5 million years, and that same light turns out to be the only tool humanity has ever had for measuring how big Andromeda truly is, how far away it sits, and how much it weighs. The way scientists turned that faint, ancient glow into precise measurements is one of the most remarkable detective stories in the history of science. In 1923, Edwin Hubble pointed the largest telescope in the world at a faint blur in the night sky and quietly dismantled everything humanity thought it knew about the scale of the universe. He did not announce a theory. He did not propose a new model. He simply measured something carefully and precisely, and the number that came back changed the cosmos overnight. But to understand what Hubble actually did and why it mattered so profoundly, it helps to go back a few years earlier to a debate that had been dividing the scientific community in a way that felt almost philosophical in its firsty implications. In 1922, respected astronomers stood before an audience at the Smithsonian Institution in Washington and argued opposite positions on one of the most fundamental questions anyone had ever asked about the universe. On one side was Harlow Shapley, who believed that the Milky Way was essentially the whole of the cosmos, an enormous galaxy that contained everything, including the faint spiral nebulae that appeared in telescope images, Andromeda among them. On the other side was Heber Curtis, who argued that those spiral nebulae were not clouds within our galaxy at all. They were entire island universes, separate galaxies in their own right, sitting at distances so vast that the Milky Way was just one among many. The question sounds almost simple now, but at the time it was genuinely unresolvable, because no one had a reliable way to measure the distance to Andromeda. And without a distance measurement, the argument could go nowhere. Both sides had reasonable evidence. Both sides had reasonable objections to the other. The debate ended without a decisive conclusion, and the question remained open. What closed it was a particular type of star that astronomers had been studying for years, without fully appreciating how useful it would turn out to be. Cepheid variable stars are stars that breathe. They expand and contract in a slow, steady rhythm, growing brighter as they swell and dimmer as they shrink, cycling through the pattern again and again with extraordinary regularity. What makes them scientifically remarkable is a relationship that the astronomer Henrietta Swan-Leavitt identified in the early 1900s while studying thousands of these stars in a nearby satellite galaxy. She noticed that the period of a Cepheid's pulsation, the time it takes to complete one full cycle from bright to dim and back to bright again, is directly and consistently related to the star's true luminosity, how much light it actually produces. A Cepheid that takes 30 days to complete a cycle is intrinsically far more luminous than one that takes 3 days. The relationship is reliable, predictable, and precise. This turned Cepheid stars into what astronomers call standard candles. If you can measure how long a Cepheid takes to pulse, you know how bright it truly is. And if you know how bright something truly is, you can calculate how far away it must be to appear as faint as it looks from where you are standing. The mathematics is straightforward. The challenge is in the observation, in detecting individual pulsing stars within a faint blur across intergalactic distances, tracking their brightness over nights and weeks and months until the pattern becomes clear. That is what Hubble spent long nights doing at the Mount Wilson Observatory in California, using the newly completed 100-inch Hooker telescope, the most powerful instrument of its kind anywhere in the world at that time. He photographed Andromeda repeatedly, building up a collection of images that could be compared and analyzed. And in those images, he began to identify what he was looking for, individual stars, whose brightness rose and fell in the distinctive rhythm of Cepheids. When he measured their pulsation periods and worked through the calculation, the answer he arrived at placed Andromeda at a distance far beyond the boundaries of the Milky Way. Not slightly beyond, not ambiguously beyond. The distance was so large that Andromeda could not possibly be a cloud or a nebula within our galaxy. It was a separate system, entirely enormous and remote, existing in its own right out in the darkness between galaxies. In that single calculation, the universe became billions of times larger than the prevailing model had allowed. The Milky Way shrank, from being the totality of existence to being one galaxy among what would eventually be understood as hundreds of billions. Everything that had seemed like the whole of the cosmos turned out to be a small neighborhood in something incomprehensibly vaster. Hubble sat with that knowledge at his desk in California in the middle of the night, with a number written in front of him that made the known universe a fundamentally different place. Once the distance was established, measuring the physical size of Andromeda became a matter of geometry. If you know how far away something is, and you can measure the angle it spans across the sky, you can calculate its actual diameter through a relationship that is simple in principle and demanding in practice. Andromeda's disk spans a considerable angle on the sky, and when that angle is combined with the known distance, the result is a diameter of approximately 220,000 light-years. Not an estimate. A measurement built on other measurements, each one tested and refined over decades of increasingly precise observation. Measuring mass required a completely different approach, because mass cannot be seen. It can only be inferred from its effects on motion. Every object orbiting another object moves at a speed that is determined by the gravitational pull acting on it, and that gravitational pull is determined by the mass of whatever it is orbiting. This means that if you can measure how fast stars and gas clouds are moving as they orbit the center of Andromeda, you can work backward through the mathematics of gravity to determine how much mass must be present at the center to produce those orbital speeds. When astronomers did this for Andromeda, they found something that did not fit. Stars in the outer regions of the galaxy were orbiting far faster than they should have been, if only the visible stars and gas were contributing to the gravitational pull. According to the known visible mass, those outer stars were moving fast enough that they should have been flung outward and escaped the galaxy entirely. But they were not escaping. They were staying in stable orbits, cycling around and around, held in place by something. The most consistent explanation, and the one that has held up across decades of further investigation, is that Andromeda is surrounded by a vast halo of matter that does not emit any form of detectable radiation, dark matter. Invisible, undetectable by any direct means currently available to science, but gravitationally real and present in quantities that significantly exceed the mass of all the visible stars and gas combined. The rotation of the outer galaxy is among the strongest evidence astronomers have that dark matter is not a theoretical convenience, but a genuine physical reality. Every generation of instruments has added precision and complexity to this picture. The James Webb Space Telescope, now operating at its observation point in space, is resolving individual stars in Andromeda with a clarity that earlier telescopes could not approach, allowing astronomers to study the age and composition of stellar populations across different regions of the galaxy in detail that was previously impossible. Each new measurement refines the numbers slightly. Sometimes it confirms what was already thought. Occasionally, it introduces a new complication, a feature that the existing models did not predict, a detail that requires explanation. The picture of Andromeda that science holds today is the result of this accumulation measurement, layered on measurement across more than a century of observation, each generation handing the next a slightly sharper image and a longer list of things that still need explaining. If you had been Hubble that night in 1923, holding in your hands the calculation that placed Andromeda beyond the boundary of the known universe, watching the cosmos expand in your mind to a scale no one had seriously considered before, what would that moment have felt like? We now know how large Andromeda is and how far it sits from us. But it does not exist alone in that darkness. It leads a family, commands a region of space, and holds a central role in a cosmic neighborhood with its own structure and its own rules. That is where the story continues. Andromeda does not stand out simply because of its size. What makes it remarkable is its position. In the particular collection of galaxies we call the local group, a gathering of more than 50 galaxies bound together by their mutual gravity and drifting through space as a loose community. Andromeda is the largest member, the heaviest. Presence, the one whose gravitational influence reaches furthest and shapes the motion of everything around it. It is not famous for being big in the abstract. It is famous for being the biggest thing in our specific corner of the universe. The local group spans roughly 10 million light-years from one edge to the other. That sounds enormous, and measured against anything in human experience, it genuinely is. But the universe is structured in layers of scale that keep expanding. And when you step back far enough to see the local group in its broader context, it shrinks quickly into something modest. The Virgo cluster, the nearest large concentration of galaxies to our own group, contains more than 1,000 galaxies. The Coma cluster holds thousands more. Entire superclusters exist that contain dozens of such clusters, each one dwarfing our small local group, the way a city dwarfs a single house on a quiet country road. If the Coma cluster, with its thousands of galaxies, represents a sprawling metropolitan area, then the local group is a village of 3 significant buildings and a few dozen smaller structures scattered around them. We are not living at the center of cosmic activity. We are living in a calm, sparsely populated rural outpost, far from the densest concentrations of matter in the observable universe. And within that quiet village, Andromeda is the largest structure, the one that sets the gravitational tone for everything else. The 2 dominant members of the local group are Andromeda and the Milky Way. Between them, these two galaxies account for the overwhelming majority of the total mass in the group. The remaining members, more than 50 galaxies in total, contribute comparatively little to the overall gravitational budget. Most of them are dwarf galaxies, small and faint, many of them satellites orbiting one of the two giants. Their paths through the local group are determined largely by the pull of the two large galaxies, rather than by any significant gravitational influence of their own. There is a third galaxy worth noting specifically. The Triangulum Galaxy, also known by its catalogue designation Messier 33, is the third largest member of the local group, and a genuine spiral galaxy in its own right, though considerably smaller than either Andromeda or the Milky Way. It sits relatively close to Andromeda in the sky, and some astronomers consider it a gravitational companion to Andromeda rather than a fully independent member of the group. Under exceptionally dark skies, far from any source of light pollution, Triangulum is technically visible to the naked eye, making it the most distant object a human being can see without optical assistance under ideal conditions. Most people never find it, and most who do are not sure what they are looking at, but it is there another galaxy, another island of stars sitting at the edge of what unaided human vision can reach. There is something quietly amusing about the cosmic address we occupy, not in a diminishing way, but in a way that puts things in perspective honestly. Our local group, which feels to us like a vast and rich collection of galaxies, is by the standards of the broader universe an unremarkable backwater. The great clusters and superclusters of the cosmos are elsewhere, dense and active, and full of thousands of galaxies, interacting in complex ways. We are in the quiet outskirts, a small group of galaxies going about their business without much company. Andromeda is the most prominent presence in that quiet place, the gravitational anchor of our village, the one that all the smaller members orbit around or are drawn toward. The structure of the universe beyond the local group proceeds in layers, each one larger than the last, by a factor that makes the previous layer seem small. The local group belongs to a broader association called the Virgo supercluster, which contains dozens of galaxy groups and clusters spread across a region roughly 110 million light-years across. The Virgo supercluster, in turn, is part of an even larger structure called Laniakea, a vast supercluster of superclusters that extends across more than 500 million light-years and contains the mass of hundreds of quadrillions of suns. And Laniakea itself is just one region within the cosmic web, the large-scale structure of the universe, formed by long filaments of matter connecting vast galaxy clusters with enormous voids of near emptiness between them. Within all of that, the local group is a small and quiet place. Andromeda is its most significant resident. One detail about Andromeda's reach within the local group is easy to overlook, but worth pausing on. The stellar halo of Andromeda, the diffuse cloud of stars that surrounds its main disk, extends outward to a distance of roughly 1.3 million light-years from the galaxy's center. That is not its dark matter halo, which stretches further still. That is the region populated by actual stars, faint and widely scattered but present. And 1.3 million light-years is a significant fraction of the 2.5 million light-years that separate Andromeda from the Milky Way. The outer edges of Andromeda's stellar halo reach toward the outer edges of the Milky Way's own halo. The two galaxies, which appear to sit apart from each other as distinct objects, are in a real physical sense already sharing space at their outskirts. They have been doing so for an immense period of time, quietly, without any dramatic announcement, their outermost stars drifting in regions of space that belong loosely to both of them at once. Andromeda's gravitational influence extends across the entire local group. The smaller galaxies within the group do not move freely in random directions. Their paths are shaped by the combined pull of Andromeda and the Milky Way, with Andromeda contributing the larger share of that influence given its greater mass. It is not merely a member of the group. It is one of the two forces that define the group's structure, hold it together, and determine where every smaller member goes. If you could step outside the local group entirely and look back at it from a distance of several million light-years, what do you think that small, loosely scattered collection of galaxies would look like against the vast structure of the universe surrounding it? Andromeda dominates the neighborhood. it lives in. But the most revealing comparison is not between Andromeda and the smaller galaxies around it. It is between Andromeda and the one neighbor that comes closest to matching it, the Milky Way. Two giants similar enough in nature to seem like variations on a single theme, but different in ways that turn out to matter enormously. There is a particular kind of insight that comes from comparison. A single object studied in isolation reveals only what it is. Place two similar objects side by side, and suddenly you see not just what each one is, but what the differences between them mean. What choices nature made in constructing one versus the other, and what those choices tell you about the forces and histories that shaped them. Andromeda and the Milky Way are the most instructive comparison available to us in the entire universe. Two large spiral galaxies sitting close enough to study in detail, similar enough to be meaningfully compared, and different enough that those differences carry real information. Both are spiral galaxies. Both have a central concentration of older stars, surrounded by a rotating disk, and within that disk, spiral arms where gas and dust are concentrated and new stars are born. Both have supermassive black holes at their centers. Both are surrounded by populations of smaller satellite galaxies. Both are embedded within halos of dark matter that extend far beyond their visible disks. At the broadest level of description, they belong to the same category of object, built according to the same general principles. But the details diverge in ways that are scientifically significant. The Milky Way is a barred spiral galaxy. This means that rather than having spiral arms emerge directly from a round central bulge, its arms connect to the ends of an elongated bar-shaped structure of stars that runs through the center of the galaxy. This bar is not a minor feature. It plays an active role in the dynamics of the galaxy, channeling gas inward toward the central region and influencing the rate at which new stars form near the core. The bar acts as a kind of funnel, redirecting material that would otherwise stay distributed through the disk and concentrating it where gravitational processes can act on it more intensely. Andromeda does not appear to have a prominent central bar. Its spiral arms emerge from a more classically rounded central bulge, giving it a somewhat different structure at its core. This difference in central architecture affects how matter moves through each galaxy, how efficiently gas reaches the central black hole, and how star formation near the center is regulated over time. Two galaxies of similar overall size and mass can have meaningfully different inner lives depending on whether a bar is present. The size difference between the two is substantial and relatively clear. Andromeda's disk spans approximately 220,000 light-years across. The Milky Way's disk is estimated at somewhere between 100,000 and 120,000 light-years, depending on where you define its outer boundary, which, as we have already seen, is not a sharp line. By disk diameter alone, Andromeda is roughly twice as wide. The star counts reinforce this picture. Andromeda is estimated to contain close to 1 trillion stars. The Milky Way holds somewhere around 400 billion. By that measure, Andromeda is more than twice as richly populated. Yet the comparison of total mass, which includes not just the visible stars but all the gas, dust, and dark matter as well, is more contested. For a long time, Andromeda was assumed to be the clear heavyweight. More recent measurements, using more sophisticated techniques to trace the motions of stars and satellite galaxies across large distances, have suggested that the total masses of the two galaxies may be closer to each other than the disk. Sizes and star counts would imply. Some studies place them within a factor of 1.5 of each other, with significant uncertainty in both directions. The science is ongoing, and each new instrument adds precision to a picture that is still being refined. Where the comparison becomes most stark is at the center. The Milky Way's central black hole, known as Sagittarius A star, has a mass approximately 4 million times that of our Sunday. That is already a number difficult to hold in mind. Andromeda's central black hole carries a mass of approximately 100 million solar masses. The difference between them is a factor of 25. These are not two objects of the same type that happen to be slightly different in scale. They represent genuinely different gravitational anchors at the hearts of otherwise comparable galaxies, and the reasons for that difference are still a subject of active research. In terms of current star formation, the Milky Way is the more active of the two. Andromeda, for all its greater size and higher star count, is forming new stars at a slower rate than our galaxy. The Milky Way is producing new stars more efficiently right now, which in a certain sense makes it the younger feeling of the two, still actively building its population, while Andromeda has settled into a quieter phase of its life. One of the stranger privileges of our position in the universe is the asymmetry of what we can see. Because we are located inside the Milky Way, embedded within its disk, we cannot see the overall shape of our own galaxy directly. We see it as a band of light across the sky because we are looking at it edge-on from the inside. To determine that it is a barred spiral, that its arms have a particular number and arrangement, that its disk is slightly warped at the edges, all of that has required indirect methods, years of mapping stellar positions and gas distributions, and using that data to infer a shape we cannot observe directly. Andromeda, on the other hand, we see from the outside. It is tilted at an angle toward us that allows us to see its disk and arms as a coherent structure, imperfectly but genuinely. This means that every time astronomers study the detailed structure of Andromeda, they are also gathering information about what spiral galaxies in general look like from a vantage point that we can never have for our own home. Andromeda serves as a kind of model, a nearby example of what we ourselves might look like to someone observing us from 2.5 million light-years away. Woven through Andromeda's outer halo are long, thin streams of stars that do not belong to any of its current organized structures. They arc through the halo in graceful curves, faint and diffuse, each one the remnant of a smaller galaxy that fell into Andromeda's gravitational domain at some point in the distant past, and was gradually torn apart and absorbed. These stellar streams are a record of Andromeda's history, written in light, a testimony to the fact that the galaxy we see today is larger and more complex than it would have been billions of years ago, having grown by incorporating others over an immense span of time. If a civilization existed somewhere within Andromeda and looked outward toward our galaxy, what would they say about the Milky Way? How would they describe its size, its shape, its star formation rate, the quiet black hole at its center? Both galaxies share something else, a secret at their core, a presence that controls the motion of everything around it without being visible. Andromeda's version of that secret is 25 times more massive than ours, and what it means for the galaxy's past, present, and future is the next part of the story. At the center of Andromeda, behind billions of stars, behind the bright swelling of the central bulge, behind layers of gas and dust that no ordinary telescope can see through directly, something sits in complete darkness. It has a mass equivalent to 100 million suns, pressed into a region of space smaller than our solar system. It produces no light of its own. It radiates no heat that any instrument has directly detected. It cannot be photographed, cannot be pointed at, cannot be shown in any image as a visible object. And yet every star in the inner region of Andromeda moves in response to it, tracing orbits whose speeds and shapes are determined entirely by its presence. It is the gravitational anchor of the entire galaxy, and it is invisible. A black hole is not a hole in the conventional sense, not an absence or an emptiness. It is a region of space where matter has been compressed to such extreme density that the gravitational field it generates overwhelms everything, including light itself. At a certain boundary surrounding this compressed mass called the event horizon, the escape velocity required to leave reaches the speed of light. Since nothing in the universe travels faster than light, nothing that crosses that boundary returns. The region inside is causally disconnected from everything outside. Whatever falls in is gone, not destroyed in any conventional sense, but removed from the observable universe permanently. The way astronomers detected the black hole at the center of Andromeda was not by looking at it directly, which is impossible, but by watching what surrounds it. Stars in the inner region of a galaxy orbit its center the way planets orbit a star, and the speed of those orbits is determined by the gravitational pull acting on them. If you measure the velocities of stars close to the galactic center and find that they are moving far faster than the visible mass of surrounding stars could account for, there is only one consistent explanation. There must be an enormous concentration of mass at the center that is not producing any visible light. In Andromeda, the stars near the core are moving at speeds that point unmistakably to a central mass of approximately 100 million solar masses. The black hole is inferred from the motion of everything around it, the way you might infer the presence of a large stone beneath a river's surface by watching how the current bends and accelerates around it. At the moment, Andromeda's central black hole is in a state astronomers describe as quiescent. It is not actively consuming large amounts of material. There are no powerful jets of plasma shooting outward along its rotation axis. There is no intense radiation pouring from its immediate surroundings. By the standards of the most energetic objects in the universe, it is essentially quiet. This is fortunate for the local group, because when a supermassive black hole is actively feeding, drawing in large quantities of gas and heating that in falling material to extreme temperatures, the energy it releases can outshine the combined light of every star in its host galaxy. Objects in this state called quasars, or active galactic nuclei, are among the most luminous things in the observable universe. Andromeda's black hole, with its mass of 100 million solar masses, would be capable of powering such an outburst if sufficient material were falling into it. For now it sits dormant, consuming only a trickle. The environment immediately surrounding the black hole is one of the most extreme places that physics permits to exist. One of the consequences of Einstein's general theory of relativity, confirmed through multiple independent lines of evidence, is that gravity affects the passage of time. The stronger the gravitational field, the more slowly time passes relative to a region where gravity is weaker. Near the event horizon of a black hole as massive as Andromeda's, this effect becomes significant. A clock placed close to that boundary would run measurably slower than an identical clock far away, not as a mechanical effect, but as a genuine property of time itself, in the presence of extreme curvature in space-time. This is not a theoretical curiosity. It is a real physical phenomenon, and it is one of the consequences of the object sitting at the center of the galaxy we can see with our naked eyes on a clear night. One of the stranger byproducts of the black hole's gravitational dominance of the inner galaxy is the existence of stars moving at extraordinary speeds through Andromeda. Occasionally, when a pair of stars passes very close to the central black hole together, the gravitational interaction can result in one star being captured into a tighter orbit, while the other is flung outward at extreme velocity, far faster than it would need to be moving to remain gravitationally bound to the galaxy. These are called hypervelocity stars, and they travel through the galaxy like projectiles, crossing enormous distances in relatively short astronomical timescales. Some of them may eventually escape Andromeda's gravitational hold, entirely drifting out into intergalactic space as solitary travelers with no galaxy to call home. The black hole did not arrive at its current mass all at once. It grew over billions of years through two main processes. The first was accretion, the gradual accumulation of gas and other material that fell into the central region and was incorporated into the black hole over time. The second was mergers. Every time Andromeda absorbed a smaller galaxy, that smaller galaxy brought its own central black hole with it. Two black holes in close proximity will eventually spiral toward each other through a process of gravitational interaction with surrounding stars, losing energy gradually until they merge into a single larger object. Over billions of years of galactic cannibalism, each absorbed companion likely contributed something to the mass of the central black hole, building it up incrementally with each merger until it reached the scale we measure today. This growth history connects directly to what lies ahead. When Andromeda and the Milky Way eventually complete their merger, the two central black holes will find themselves in the same galaxy for the first time. Initially, they will be separated by enormous distances, orbiting the combined gravitational center of the merged system. Over time, through interactions with surrounding stars, they will lose energy and spiral closer to each other. The final stage of that spiral, when the two objects are close enough that gravitational wave emission becomes the dominant mechanism of energy loss, will produce ripples in space-time, propagating outward across the local group and beyond. The merger of two black holes weighing 4 million and 100 million solar masses respectively will be one of the most energetically significant gravitational wave events in the history of our cosmic neighborhood. If Andromeda's central black hole were to suddenly transition from its current quiet state into active feeding, consuming material at the rate of the most energetic quasars known, what do you think we would observe from Earth? The black hole is not the only thing hiding in Andromeda's depths. Around it and around the entire galaxy exists a family of smaller companions whose fates are being decided right now by the same gravitational force that shaped the black hole itself. How Andromeda treats those companions reveals something true and not entirely comfortable about the nature of every large galaxy in the universe. Andromeda does not travel alone. It moves through the local group at the center of its own system, a collection of smaller galaxies that orbit around it, drawn by its gravity, shaped by its presence, and in many cases, slowly being dismantled by it. To look at Andromeda in a deep telescope image is to see not just a galaxy but a gravitational domain, a region of space where one massive object has gathered companions around itself and is with complete indifference and perfect physical consistency determining their futures. The two most prominent companions are visible even in modest amateur telescopes, appearing as faint smudges near the main disk of Andromeda. The first is designated Messier 32, a small compact elliptical galaxy sitting remarkably close to Andromeda in the sky. What makes Messier 32 unusual is its density. For its size, it contains an extraordinary concentration of stars packed tightly together, giving it a brightness that seems disproportionate to its small, apparent extent. The leading explanation for this compactness is not that Messier 32 was always this dense. It is that Messier 32 was once significantly larger, a more substantial galaxy with extended outer regions of stars and gas. Through repeated close passages near Andromeda over billions of years, the gravitational tides generated by the larger galaxy progressively stripped away those outer layers, leaving behind only the dense central core that proved too tightly bound to be easily pulled apart. What we see today as Messier 32 may be the stripped remnant of something that was once considerably more impressive. The second prominent companion is Messier 110, a diffuse elliptical galaxy with a softer, more spread-out appearance than Messier 32. Unlike the compact density of its companion, Messier 110 shows elongated wisps and faint extensions trailing away from its main body structures that reflect the ongoing gravitational interaction with Andromeda. It has not been stripped as severely as Messier 32 appears to have been, but the marks of the relationship are visible in its shape. A galaxy that has been gently but persistently tugged and stretched by a neighbor far more massive than itself. Beyond these two, Andromeda is surrounded by dozens of additional satellite galaxies, most of them dwarf galaxies, so faint and diffuse that they were entirely unknown until recent decades. The improvement in telescope sensitivity and the development of wide-field survey cameras capable of detecting extremely low surface brightness objects has steadily expanded the known population of Andromeda's satellites. Some of these newly discovered dwarfs are so dim and extended that they barely stand out against the general background of space. Detecting them requires careful statistical analysis of star counts over large areas of sky, looking for subtle overdensities of stars moving together that would not be present if those regions were simply empty space. Each new discovery adds a member to the family, and the family has turned out to be considerably larger than earlier, less sensitive observations suggested. Threading through Andromeda's outer halo, alongside these surviving satellite galaxies, are the stellar streams, long, thin arcs of stars, following paths that trace the orbits of galaxies that no longer exist as coherent structures. These streams are the remains of companions that passed too close to Andromeda and were torn apart by tidal forces, their stars pulled free and strung out along the orbital path they shared with their parent galaxy. Over hundreds of millions or billions of years, these streams persist as coherent structures gradually widening and dispersing, but still detectable as organized overdensities of stars in the halo. Each stream is a record of a specific event, a specific galaxy that came too close at a specific time and did not survive the encounter. Reading the streams is a form of archaeology, reconstructing a history of mergers and absorptions that shaped Andromeda into what it is today. The fate of a satellite galaxy depends heavily on how close it orbits to Andromeda. This relationship is consistent and in some ways unsparing. Satellites that orbit within the inner regions of Andromeda's gravitational domain are exposed to a combination of tidal stripping and a pressure effect from the hot, diffuse gas that fills the halo of the larger galaxy. This pressure progressively removes the cold gas from the smaller galaxy, the gas that would otherwise collapse into new stars. Once a satellite loses its gas, reservoir star formation ceases. The existing stars continue to age and evolve, but no new ones replace them. The galaxy gradually becomes a population of older, redder stars, its active life effectively over while it continues to orbit its massive host. Satellites orbiting at greater distances from Andromeda are less exposed to these effects. They retain more of their gas, continue forming stars, and remain more actively alive in a galactic sense. The Milky Way is engaged in an identical process. The Sagittarius dwarf galaxy, a small companion of our own galaxy, is currently being disrupted and absorbed. Its stars have been stretched into long streams that wrap multiple times around the Milky Way, and the dwarf galaxy itself is losing coherence with each orbit as our galaxy's tidal forces pull it further apart. We are not simply potential future victims of Andromeda's approach. We are already doing to our own satellites what Andromeda is doing to its. The process of large galaxies growing by absorbing smaller ones is not unique to Andromeda. It is how all large galaxies in the universe grow. The Andromeda we observe today, with its 220,000 light-year disk, its 1 trillion stars, and its 100 million solar mass black hole, did not emerge from the early universe in this form. It grew. Each absorbed companion added stars to its halo, contributed mass to its gravitational budget, and potentially delivered a black hole to merge with its central one. The stellar streams and the dense remnant cores of stripped satellites are not imperfections in an otherwise clean structure. They are the evidence of the process by which Andromeda became what it is. Knowing that both Andromeda and the Milky Way are actively consuming smaller galaxies right now, does that change the way you think about what it means for a galaxy to exist? Andromeda has grown by absorbing others across billions of years. Now it faces something it has never encountered before. A collision not with a small companion it can quietly dismantle, but with a galaxy of comparable scale. And that collision has not been waiting patiently in the future. In a precise and technical sense, it has already begun. The dark matter halos of Andromeda and the Milky Way have already made contact. This is not a prediction about something that will happen at some distant point in the future. It is a description of what is happening right now at this moment as you read these words. The outermost gravitational envelopes of the two largest galaxies in the local group are already overlapping, already interacting, already exchanging influence across the boundary where one ends and the other begins. The collision that most people imagine as a future event, something safely billions of years away, and therefore comfortably abstract, has, in the most technically precise sense, already started. The evidence that Andromeda is moving toward us comes from light itself. When a source of light moves toward an observer, the waves of that light are compressed slightly, shifting the spectrum of the light toward shorter wavelengths toward the blue end of the spectrum. When a source moves away, the waves stretch, shifting the spectrum toward red. This effect, called the Doppler shift, allows astronomers to measure the velocities of distant objects relative to Earth with considerable precision, simply by analyzing the color of their light. Most large galaxies in the observable universe show redshifts, their light stretched toward the red end of the spectrum because the expansion of space itself is carrying them away from us. Andromeda is one of the very few large galaxies that shows the opposite. Its light arrives slightly compressed toward the blue, meaning it is moving toward us rather than away. Its local gravitational relationship with the Milky Way, strong enough to overcome the general expansion of space in our region of the third universe. The measured approach velocity is approximately 110 kilometers every second. That sounds fast. By any standard of human experience, it is fast. But across a separation of 2.5 million light-years, even 110 kilometers per second is a pace of almost geological patience. At that rate, the full merger of the two galaxies, the point at which they have passed through each other, fallen back together and finally settled into a single combined structure, will not be complete for approximately 4 billion years. The process will unfold in stages, each one lasting hundreds of millions of years. The halos have already begun their overlap. Next, after roughly 2 billion years, the visible disks of the two galaxies will begin to interact directly, their stars and gas clouds entering each other's gravitational fields in earnest. The galaxies will then pass through each other, not colliding in any solid object sense, but interpenetrating their stars, threading between each other across the vast, empty spaces that separate individual suns. After that first passage, the galaxies will separate again, drawn apart by their residual momentum before gravity pulls them back together for a second encounter. Over successive interactions, energy will be redistributed, orbits will be scrambled, and the two systems will gradually lose the coherence of their original spiral structures. Eventually, over a timescale of several billion years from now, they will merge completely into a single entity. Here is something that tends to surprise people when they first encounter it. Despite being described as a collision between two enormous galaxies, the actual probability of any individual star from Andromeda physically striking any individual star from the Milky Way during the entire process is extraordinarily small. The reason is the same reason that made measuring Andromeda so challenging in the first place. The distances between stars within a galaxy are immense. Even in the densest regions of a galactic disk, stars are separated from each other by distances measured in light-years. When two galaxies pass through each other, those vast interstellar gaps mean the stars of one galaxy move through the gaps between the stars of the other, with almost no direct encounters. It is somewhat like imagining two enormous swarms of widely spaced particles passing through each other. The swarms interact gravitationally as systems dramatically rearranging the orbits of their members, but the individual particles rarely touch. Our Sun, along with any planets that remain in orbit around it at that distant future point, will most likely pass through the entire process without suffering any direct stellar collision, simply settling into a new orbit within the merged galaxy. What will be genuinely and dramatically affected is the gas. Unlike the stars, the clouds of gas distributed through the disks of both galaxies will collide directly with each other, compressing and heating as they meet. Compressed gas cools and collapses under gravity, and collapsing gas forms stars. The merger of Andromeda and the Milky Way will trigger waves of star formation on a scale neither galaxy is currently experiencing, lighting up the combined system with vast numbers of newly born stars and the glowing nebulae surrounding them. The sky visible from any world surviving through that period will be transformed, crowded with structures that bear no resemblance to anything observable today. Long before the disks make contact, the change in the sky will be gradual but unmistakable. Over millions of years, Andromeda will grow larger in the night sky, its faint blur brightening and expanding as the distance between the galaxies decreases. What is now a modest smudge requiring dark skies and careful attention to find will become a prominent feature, visible even under less than ideal conditions. Eventually, it will dominate the sky, its spiral structure visible to the naked eye, its arms spanning an arc that dwarfs any other object in the heavens. Then the two systems will begin to overlap in the sky. as well as in space, their stars intermingling in the view from any surviving world, the familiar band of the Milky Way merging into something far more complex and crowded. The final product of the merger, the object that astronomers have informally called Milkomeda, will not resemble either of its parent galaxies. The spiral structure of both will be lost during the violent rearrangement of orbits. What will remain is a large elliptical galaxy, smooth and rounded without spiral arms, without the organized rotating disk structure that currently defines both Andromeda and the Milky Way. Elliptical galaxies of this type tend to have consumed or expelled most of their available gas during the energetic processes of their formation, leaving them as relatively quiet populations of older stars with little ongoing star. To formation. Milkomeda will be more massive than either of its progenitors, but in many ways less dynamic, a large and settled structure that has burned through the fuel for its most active phase. At the center of the merged galaxy, the two supermassive black holes will eventually find each other. Initially separated by an enormous distance within the new combined system, they will sink toward the gravitational center through interactions with surrounding stars, gradually spiraling closer over millions of years. When they finally merge, the energy released as gravitational waves will represent the most powerful such event the local group has ever produced. Ripples in the fabric of space-time propagating outward in every direction. If descendants of humanity were present 4 billion years from now to watch the night sky transform across their lifetimes, what name do you think they would give to the new galaxy that emerged from the merger of their ancient home with its longtime neighbor? The collision will happen regardless of anything we might think or feel about it. But the question that sits beneath all of this physics is not really about what will happen to the galaxies. It is about what any of this means to us, the brief and small creatures who happen to exist right now in this particular moment in one corner of one of the galaxies involved. We are smaller relative to Andromeda than a single atom is relative to the Earth, not metaphorically smaller. Proportionally, genuinely, measurably smaller by a margin that the comparison barely captures. A human body contains something on the order of 7 billion atoms. The number of atoms in a person, relative to the size of a person, is itself an almost incomprehensible ratio. And yet that ratio is still not as extreme as the ratio between a human being and a galaxy 220,000 light-years across. We are, by any physical measure, vanishingly small in comparison to what we have spent this entire story describing. And we understand it anyway. That is the strange part. A human brain weighs approximately 1.4 kilograms. It sits inside a skull on a planet that is itself a small rocky object orbiting an unremarkable star in the outer regions of a galaxy that is, as we have established, smaller than its nearest large neighbor. That brain, that 1.5 kilograms of biological tissue can form a concept of a galaxy. It can hold in mind the distance of 2.5 million light-years, the timescale of 4 billion years, the mass of 100 million solar masses. It cannot feel these things the way it feels warmth or hunger or the texture of something in its hands. But it can reason about them, build models of them, test those models against evidence, and arrive at descriptions of distant objects that are accurate enough to be useful and surprising enough to be humbling. Nothing else in the known universe has been observed doing this. There is something else worth noting about the relationship between us and Andromeda that goes beyond the matter of size and understanding. We are not merely observers looking at something external and foreign. The carbon atoms in your body were not present when the universe began. They were synthesized inside stars, forged from lighter elements through the nuclear reactions that power stellar cores. When those stars reached the end of their lives and exploded as supernovae, they scattered those heavy elements outward into the surrounding space. Over billions of years, that material was gathered by gravity, incorporated into new clouds of gas and dust, and eventually became part of new stars and the planets around them, including the planet you are currently standing or sitting on. The iron in your blood, the calcium in your bones, the oxygen in every breath you take, all of it passed through the interior of at least one star before it became part of you. Inside Andromeda, that same process is happening right now. Stars are fusing hydrogen into helium, helium into carbon and oxygen, and heavier elements still. Supernovae are scattering those elements into the interstellar medium. Gas clouds are collapsing to form new stars. The chemistry occurring in the galaxy we can see with our naked eyes on a dark night is the same chemistry that produced every atom in your body. We are not looking at Andromeda from the outside. We are made of the same process that Andromeda is made of, expressed at a different scale in a different location. The history of human understanding of Andromeda is a history of repeatedly discovering that we are smaller and less central than we previously thought, and somehow continuing to look anyway. In the year 964, the Persian astronomer Abd al-Rahman al-Sufi described a small cloud in that part of the sky, carefully noting its position relative to nearby stars. He could not have known what it was. In the year 1764, Charles Messier catalogued it as a fuzzy patch to be avoided by comet hunters, a curiosity with no known nature. In the year 1923, Edwin Hubble proved it was a separate galaxy, millions of light years away, and in doing so, expanded the known universe overnight. Each step in that progression required revising downward our estimate of our own importance in the overall scheme of things. The universe was not centered on Earth. It was not centered on the Sunday. It was not even centered on the Milky Way, and the Milky Way itself was not the largest galaxy in its own neighborhood. None of this made people stop looking. If anything, each revision has made the looking more purposeful. There is a reasonable argument that the scale of galaxies, far from making individual human concerns seem meaningless, actually provides a useful form of perspective. The problems that feel urgent and overwhelming at human scale, the anxieties of daily life, the pressures of immediate circumstance, do not disappear when measured against the timescale of galactic mergers. But they do find their proper proportion. A galaxy takes 4 billion years to complete a merger. A human life is measured in decades. Neither of these facts diminishes the other. They simply belong to different scales of existence, and knowing both scales simultaneously is something only creatures like us appear to be capable of. Andromeda raises questions it cannot itself answer. Within its 1 trillion stars, the number of planets is unknown, but almost certainly enormous, given what we have learned about the prevalence of planetary systems around stars in our own galaxy. Whether any of those planets carry life, and whether any of that life has developed the capacity to look outward and ask questions about the universe it finds itself in, is something we do not know. If such beings exist somewhere within Andromeda, they are looking out at a universe from a vantage point 2.5 million light-years from ours. If they have instruments powerful enough to detect light from our direction, they are seeing our solar system not as it is, but as it was 2.5 million years ago, long before any of the civilizations, languages, or accumulated. Knowledge that make this story possible had come into existence. Knowing that you are made of the same material as the stars burning inside Andromeda right now, forged in the same kinds of stellar cores, scattered by the same kinds of explosions, gathered by the same gravity, does that change anything about how you think of yourself in relation to the universe around you? After everything that this story has covered, all the measurements and mergers and black holes and ancient light, there is one final thing that the whole journey has been pointing toward. And it turns out to be simpler than almost anything else we have discussed. Tonight, if the sky above you is dark enough, something is falling toward Earth. Not meteorites, not radiation from a distant explosion. Photons. Individual packets of light, each one carrying energy that was released inside a star located 2.5 million light-years away, each one having traveled across intergalactic space for 2.5 million years to arrive at this particular moment, on this particular night, at the thin shell of atmosphere surrounding this particular planet. They have been in transit since before our species existed. They passed through the cold emptiness between galaxies while our ancestors were still learning to shape stone. They crossed the remaining distance while every civilization in human history rose and fell and was replaced by the next. And now tonight, they are here. They do not choose where they land. That is perhaps the first thing worth understanding about these photons. They arrive without preference, without direction, in any intentional sense, spreading outward from Andromeda in every direction simultaneously, a continuous sphere of light expanding across space at the speed that light travels. When they reach Earth, they fall on everything equally. They land on rooftops and on the surfaces of roads. They sink into the dark water of oceans and are absorbed by the leaves of trees and the soil of fields. They touch the closed eyelids of people who are already asleep and the open eyes of people who happen to be looking upward at the right moment with enough darkness around them to let the signal register. The photons make no distinction between these outcomes. They simply arrive, and whatever receives them receives them. But for the ones that reach an open eye on a dark night, something specific happens. A 2.5 million year journey ends. The energy carried across all that distance and all that time is absorbed by a cell in the retina, converted into an electrical signal, and sent along the optic nerve to a brain that interprets it as a faint smudge of light in a particular region of the sky. The photon ceases to exist as a photon. Its journey, which began in a star you will never visit in a galaxy you can barely see, is over. And the entire record of that journey now exists only in the fact that you noticed something. Think for a moment about everything that faint smudge actually is, given what this entire story has been building toward. It started as a blur, easy to overlook, easier still to mistake for a wisp of cloud or a smear of atmospheric haze. But beneath that modest appearance sits a galaxy that stretches 220,000 light-years from edge to edge, containing close to 1 trillion stars, anchored at its center by a black hole weighing 100 million times the mass of our Sunday. It is a living system breathing through cycles of star birth and death, its spiral arms not solid structures but persistent waves of density rolling through a disk of gas and dust and stellar fire. It is a time machine showing us not what it is, but what it was, its light. A 2.5 million year old image of something that has continued to evolve in ways we cannot yet see. It is a traveler approaching us at 110 kilometers every second, its dark matter halo already overlapping with our own. The opening act of a merger that will eventually dissolve both galaxies into something neither of them currently resembles. And it is a record, its stellar streams and asymmetric arms and rings of disturbed dust, carrying the accumulated evidence of billions of years of collisions and absorptions and gravitational encounters that shaped it into the object we observe today. All of that is contained in the light that ends its journey in your eyes on a clear night. Andromeda does not know we exist. This is worth stating plainly without any softening. The galaxy is not sending us a message in any purposeful sense. It has no awareness of the planet it is approaching, no knowledge of the species on that planet that has spent centuries trying to understand what it is. The light it produces is the byproduct of nuclear reactions in stellar cores, nothing more. It goes out in all directions because that is what light does not, because any of it was aimed here. The fact that some fraction of it reaches Earth, and some further fraction of that reaches human eyes, and some further fraction of that is interpreted by human minds into an understanding of what Andromeda actually is, that entire chain of events is something we brought to the encounter, not something the galaxy provided. And that, quietly, is the most remarkable part of the whole story. Every piece of knowledge gathered about Andromeda across the centuries came from the same basic act. Someone looked up and paid attention to something that most people walked past without noticing. Abd al-Rahman al-Sufi, in the 10th century, working through the night with careful eyes and a commitment to recording what he saw, noted a small cloud where others saw nothing worth mentioning. Generations of astronomers after him measured and catalogued and debated the nature of that cloud without being able to resolve the question. Edwin Hubble, in a cold observatory in the mountains of California in 1923, stayed up through long nights, tracking the brightness of individual stars within that blur, until he had enough data to calculate something that changed the scale of the known universe. None of them were compelled to do this by any external force. The galaxy was not asking to be understood. The curiosity that drove the looking was entirely human, entirely internal, entirely a product of a species that finds itself unable to leave questions unanswered. The meaning of Andromeda, if that word applies here, does not live inside the galaxy. It lives in the act of looking toward it, in the question that arises when someone pauses on a dark night and notices the smudge and wonders what it is. In the willingness to follow that question, as far as it leads through measurement and calculation, and inference through centuries of accumulated effort by people who mostly never met each other and who built on each other's work, across generations. The galaxy provided the raw material, the photons, the signal. Everything else, the understanding, the sense of scale, the recognition of what it means that such an object exists and that we can perceive it at all that came from us. There is a practical dimension to this that is easy to forget in the middle of all the cosmological abstraction. Andromeda is visible tonight, not in a theoretical sense, not in the sense that it exists and its light is technically present in the atmosphere, but genuinely visible, findable, something you can actually go outside and see with no equipment beyond your own eyes, and enough patience to let them adjust to the darkness. The process takes about 20 minutes. 20 minutes of standing outside without looking at any bright source of light, letting the cells in your retina that are sensitive to low light levels gradually reach their full sensitivity. After that, in a sky dark enough to show the Milky Way, the constellation of Andromeda is not difficult to locate, and within it, slightly off to one side of the main pattern of stars, there is a soft oval blur that does not look like a star, and does not look like anything else in the sky. That blur is a galaxy. The photons reaching your eyes when you look at it left their source 2.5 million years ago. The cells in your retina that absorb those photons are the end point of a journey that no other destination along the way could have made meaningful in the way that a conscious, curious, questioning mind makes it meaningful. You are not passively receiving a signal. You are completing a circuit that has been open for 2.5 million years, waiting for something on this end, capable of understanding what it is receiving. The question that Andromeda implicitly poses, the one that all of this has been circling around, is not really about size. It is not asking whether you can comprehend 220,000 light-years or 1 trillion stars or 4 billion years of future collision. Those numbers are beyond genuine comprehension for any human mind, and that is fine. The question is something simpler and stranger. In a universe this vast, operating on timescales this long, shaped by forces, this impersonal, the fact that something exists that can notice any of it, that can look up at a smudge of ancient light and trace it back to its source and forward, to its future and inward to its structure, is that not itself something worth pausing over? The universe did not arrange itself to produce observers. There is no evidence that consciousness was a goal of any cosmic process. And yet here we are, the product of the same star formation and supernova enrichment and planetary accretion that fills Andromeda's disk, somehow arranged into a configuration that asks questions about galaxies. The carbon in your body and the carbon in Andromeda's stellar nurseries share the same origin story. The difference is that some of the carbon on this side of the 2.5 million light-years ended up in a brain, and that brain looked across the distance and wanted to know what was over there. Andromeda will continue its approach, whether we watch it or not. The merger will unfold on its own timescale, regardless of whether anyone on Earth ever thinks about it again. The black holes at the centers of both galaxies will eventually find each other and merge and send gravitational waves across the local group, whether or not any mind is present to register the event. The universe does not require our attention to proceed, but we can give it our attention anyway. We can step outside on a clear night and let our eyes adjust, and find the faint blur in the constellation that ancient storytellers wove into their myths long before anyone knew what it was. We can look at it not as a test of astronomical knowledge, but as what it actually is, a personal encounter with 2.5 million years of traveling light that has arrived specifically here on this night and will be absorbed, specifically by the eyes that are looking at it, and by no others. Andromeda does not ask whether you are large enough to understand it. It does not ask whether you have the right background or the right instruments or the right vocabulary for what you are seeing. It simply shines. It has been shining in that patch of sky for longer than our species has existed, and it will continue shining long after every structure we have ever built has been returned to dust. All it has ever done is send its light outward into the dark, in all directions, without preference or purpose, waiting for nothing. The waiting has always been on our side. After everything you now know about Andromeda from the faint smudge, it appears to be to the trillion-star giant it actually is. From its ancient light to its inevitable future, what is the first thing you want to do?